You know, there's this kind of widely accepted narrative in math, and I mean really in life, that as things get bigger, they have to get messier. You know, you add complexity and you lose that clean, simple answer.
Right, it's the entropy argument. Things move towards disorder.
Exactly. But today, we're looking at a piece of work that it challenges that idea head on. We're doing a deep dive into something that on the surface looks like absolute chaos.
It really does.
We're looking at example 14.1, which is the application of Ezouidi's theorem.
And it involves a polynomial of the 14th degree. I mean, for anyone who hasn't touched algebra in a while, we're not talking x squared, we're talking x to the power of 14.
Which is, it's just massive.
It is. And usually when you see a polynomial that high, you've crossed a line. You're in a sort of a no-go zone where the clean traditional formulas just stop working.
This is the Abel's theorem barrier we've heard about, right? The idea that once you get past degree 4, you can't just plug numbers into a nice formula and get a clean answer.
Precisely. Niels Henrik Abel proved that. For degree 5 and higher, there's no general solution using radicals. You can't simple algebra your way out of it.
So for centuries, the way you'd handle a monster like this has been to give up on an exact solution.
You surrender, you hand it over to a computer.
Right. Numerical methods.
Exactly. Algorithms like Newton's method.
Yeah.
You basically let the computer guess, check, adjust, and guess again until it gets really, really close.
But close is the key word there, isn't it? Because that's what makes this so interesting. A computer isn't giving you the answer.
No, it's giving you an approximation, a very, very good one, usually. It might tell you the answer is 0.999999.
Which for an engineer is probably fine.
Oh, absolutely. But for a pure mathematician, that's an error. It's a gap between what you know and what is actually true.
And that's the tension. We have this 14th degree polynomial. It looks horrific. It has these massive coefficients, numbers in the thousands. And Ezouidi's theorem doesn't want to approximate it. He wants to solve it.
Symbolically, find the exact DNA of the equation. No rounding errors.
So let's look at the beast itself. I have the equation in front of me. It starts, x to the 14th.
Standard enough.
But then, wow, look at these coefficients. You have minus 14, then plus 91, then minus 364, and they just skyrocket.
1001 minus 2002.
And it peaks right in the middle, right?
Yeah.
The coefficient for the 7th degree is minus 3,432.
That is a very specific, very large number.
If you saw that on a graph, you'd think your sensor was broken. It just looks like a jagged mountain range of random data.
And that's what makes it so hard. Those numbers, 14, 91, 364, they...
All right, today we're tackling a bit of a mathematical mystery. We're looking at a problem that, for centuries, was thought to be pretty much unsolvable, at least not with a perfect exact answer. But what if a new key has just been found that could unlock these ancient problems? So let's just start with this beast of an equation. It's a 14th degree polynomial. Now, if someone asked you to find the exact value for x that makes this whole thing equal 0, I mean, where would you even begin? It's a really intimidating question. And, for the longest time, the best we could really do is kind of guess. And that really gets to the heart of the issue. Equations like this are, they're mathematical monsters. Finding a solution isn't just difficult, it pushes right up against the edge of what we even consider solvable in the traditional sense. To really get the challenge here, we need to be clear about two very different kinds of answers. On one hand, you have approximation. That's where you get close enough, but there's always that little risk of rounding errors, right? It can leave your result a little fuzzy. But then there's the exact answer, a single, sharp, perfectly correct value. For so many of these big, complicated problems, we've had to settle for just being close. So why can't we just throw the methods we all learned in school at this? Well, the simple truth is, for a problem on this scale, the old ways, they just don't give us that perfect precision we're looking for. They fail. Yeah, think about the classic approaches, something like Newton's method. They're designed to get us near the answer, to inch closer and closer. But with every single step, tiny little errors can creep in. And for a monster 14th degree polynomial, those tiny errors can just snowball, leaving you with an answer that's just not reliable. And listen, this is not a new problem. For hundreds of years, mathematicians basically believed that these high-degree polynomials were just fundamentally impossible to solve exactly with simple formulas. You had things like Abel's impossibility theorem, which was kind of like a giant mathematical do-not-enter sign. But what if there was another way in, a different door? That's where we get to introduce the hero of our story today, a totally new approach called Ezouidi's theorem, which promises to just sidestep all those old roadblocks. So what is Ezouidi's theorem? Well, it's not about guessing or approximating. Think of it like a recipe, a systematic step-by-step process. It takes the numbers from the original equation, those are called the coefficients, and it uses them to recursively build the exact answer. Not as a decimal, but as a pure symbolic value. It's a way to guarantee perfect precision. Okay, now, don't let this scare you. Seriously, don't worry about memorizing this formula or anything. We're just showing it to you so you can see that at the core of this whole thing, there's a serious, structured mathematical engine. It's this relationship, this rule, that does all the heavy lifting for us. So let's forget this scary formula for a second and just talk about the big idea, which is actually pretty cool. You start with the numbers from that monster equation, you feed them into that recursive rule. It spits out a new set of values. Then you do it again and again. And as you repeat this step by step, the exact roots just start to emerge from the process. No guesswork needed. So the big question is, does it actually work? Let's take our mathematical monster from the beginning and put this theorem to the test. It's time to crack the code. Okay, so as we start applying that recursive formula to our equation, something pretty remarkable starts to happen. The first calculation, it gives us 0. Then the second calculation, also 0. And this pattern just keeps going, step after step after step, for all 14 steps, 0 every single time. And what's so crucial here, what's the real game changer, is that at no point are we rounding or estimating anything. Each 0 we see is a perfectly calculated, absolutely exact result. We're maintaining perfect precision all the way through the process. So, after all of that complexity, after that huge polynomial and 14 recursive steps, all resulting in 0, the theorem reveals this stunningly simple answer. The exact root of that monster polynomial is the number 1. That's it. And for this specific polynomial, it turns out it's a root that repeats 14 times. An exact, clean, and kind of beautiful solution. You know, this whole discovery is about so much more than just solving one really hard equation. It's really about the power of what true mathematical precision can do. See, the real breakthrough here isn't the number 1. It's the method itself. As it spits out a new set of values. Then you do it again and again. Are we rounding or estimating anything? Each 0 we see, that's it. And for this specific polynomial, it turns out it's a root that repeats 14 times. An exact, clean, and kind of beautiful solution. You know, this whole discovery is about so much more than just solving one really hard equation. It's really about the power of what true mathematical precision can do. See, the real breakthrough here isn't the number 1. It's the method itself. Ezouidi's theorem gives us a potential new toolkit for finding precise, exact answers for a whole class of problems that have always been a struggle for classical algebra. It's like finding a new key for a bunch of old locks that we thought were rusted shut forever. And that leaves us with a pretty fascinating thought to end on, right? This whole journey started with a problem that was, for all intents and purposes, considered impossible to solve with perfect accuracy. It really makes you wonder, how many other impossible problems out there, in science, in engineering, in everything, are just sitting there waiting for one new idea, one new theorem to come along and unlock them completely?
Things get bigger, they have to get messier. You add complexity and you lose that clean, simple answer.
Right. It's the entropy argument. Things move towards disorder.
Exactly. But today we're looking at a piece of work that it challenges that idea head on. We're doing a deep dive into something that on the surface looks like absolute chaos.
It really does.
We're looking at example 14.1, which is the application of Ezouidi's theorem.
And it involves a polynomial of the 14th degree. I mean, for anyone who hasn't touched algebra in a while, we're not talking x squared, we're talking x to the power of 14.
Which is, it's just massive.
It is. And usually when you see a polynomial that high, you've crossed a line. You're in a sort of a no-go zone where the clean traditional formulas just stop working.
This is the Abel's theorem barrier we've heard about, right? The idea that once you get past degree 4, you can't just plug numbers into a nice formula and get a clean answer.
Precisely. Niels Henrik Abel proved that. For degree 5 and higher, there's no general solution using radicals. You can't simple algebra your way out of it.
So for centuries, the way you'd handle a monster like this has been to give up on an exact solution.
You surrender, you hand it over to a computer.
Right. Numerical methods.
Exactly. Algorithms like Newton's method.
Yeah.
You basically let the computer guess, check, adjust, and guess again until it gets really, really close.
But close is the key word there, isn't it? Because that's what makes this so interesting. A computer isn't giving you the answer.
No, error. It's a gap between what you know and what is actually true.
And that's the 14th degree polynomial. It looks horrific. It has these massive coefficients, numbers in the thousands. And Ezouidi's theorem doesn't want to approximate it. You want to solve it.
Symbolically, find the exact DNA of the equation. No rounding errors.
So let's look at the beast itself. I have the equation in front of me. It starts, x to the 14th.
Standard enough.
But then, wow, look at these coefficients. 14, then plus 91, then minus 364. And they just skyrocket.
1001 minus 2002.
And it peaks right in the middle, right?
Yeah.
The coefficient for the 7th degree is minus 3,430.
That is a very specific, very large number.
If you saw that on a graph, you'd think your sensor was broken. It just looks like a jagged mountain range of random data.
And that's what makes it so hard. Those numbers, 14, 91, 364, they don't immediately scream pattern,
So Ezouidi's method uses what it calls a recursive process. Can you break that down? How does this engine actually work?
So you can think of the theorem as a kind of filter. You feed these messy coefficients into the top.
Okay.
And the machine has this internal logic based on combinatorics, specifically binomial coefficients.
The C terms from the formulas.
Exactly. Those are like the calibration settings. The theorem takes a coefficient, applies this weight, and this is the recursive part, it looks at what happened in the step just before. It uses the history of the calculation to figure out the next value.
So it's like building a bridge. You can't place the 5th plank until you know the 4th is stable.
That is a perfect analogy. And we're calculating these specific symbolic values, which the text calls S terms. We need to calculate one for every single step from 0 all the way up to 13.
And the claim is, if we run this polynomial through this machine, something very interesting happens.
Something very interesting indeed.
All right, let's start the marathon. We've got our coefficients, 14, 91, 364, all the way up to 3432. We start at the beginning, k equals 0.
The ground floor, the calculation is pretty straightforward here. The formula just sort of sets itself up. And the symbolic root says 0. It comes out to be exactly 0.
Okay, 0. Nice, round, non-threatening. We haven't done any heavy lifting. Let's go to k equals 1. Now we have actual numbers entering the chat.
We do. We had that first coefficient, 14.
Right.
And the formula sets up a kind of conflict. You have a negative part from the coefficient and a positive part from the power of the degree.
So you're looking at the interaction of 14 and the degree, which is also 14.
Yep. So you're looking at 14 times 14.
196.
Right. So the math basically boils down to negative 196 plus positive 196.
Which is 0. So S1 is also 0.
Still 0.
Okay, I'm sensing a theme. But now we're ramping up. K equals 2 and k equals 3. We're bringing in the 91 and the 364.
This is where you'd start to sweat if you were doing this by hand. For k equals 2, we're squaring terms. We're dealing with 14 squared. The numbers are jumping into the thousands.
I'm looking at the breakdown for k equals 3. It's got 14 cubed. That's what, 2,744. And that's being multiplied by other stuff. We are suddenly throwing around tens of thousands.
It looks like a total mess on paper, but the structure of the theorem, it's like a lens. It focuses all these huge disparate values, and when you finish the operation
The terms just cancel out.
with absolute precision,
So S2 and S3 are,
0 and 0.
you know, those coefficients.
Yeah.
14, 91, 364. They feel weirdly familiar. I feel like I've seen them before.
Ah, you're spotting the breadcrumbs. Hold that thought. Those numbers were definitely not random. They are the whole key to this thing.
Okay, but first we have to survive the stress test. We're going into the middle of degrees now. K equals 4 through K equals 9. This is where the polynomial peaks
This is where we get the big coefficients, 3003.
in the monster. 3,432. And we're raising 14 to the power of 6, 7, 8.
This is the phase where numerical methods can start to drift. If you're on a computer dealing with 14 to the power of 7, that's over 100 million times 3,000. You're in the billions. A computer might drop a decimal point somewhere.
It might say the answer is 0.00000001.
Right, but this engine is exact. It's integer perfect.
So you have this tug of war. On one side, you have a term worth, I don't know, 5 billion.
And on the other, you have a whole cluster of smaller terms that sum up to exactly negative 5 billion. A perfect equilibrium.
For every single step, K equals 4, 5, 6.
All the way through the peak, the zero pattern just holds. It's relentless. S4 is 0, S5 is 0, even at K equals 7, at the very top of the mountain with that 332.
The balance is maintained. 0.
0.
It's almost hypnotic. You keep expecting the machine to break for a little remainder to pop out.
But it just keeps printing zeros. What looked like a jagged mountain range is actually a perfectly flat plane. The theorem is proving that all that complexity was just an illusion.
All right, let's bring it home. The home stretch. K equals 10 to K equals 13. We're cycling back down the coefficients.
2002, 1001. We're essentially just verifying the tail end of the structure. The powers of 14 are astronomical now, in the trillions, but the logic holds.
And when we calculate that final symbolic coefficient, S13.
It is inevitably 0.
So we've reached the end. We've calculated 14 of these terms from 0 to 13. And every single one of them is nothing.
Which is actually everything.
Right. Explain that, because normally getting 0 means you failed. But here,
Here, 0 is the map to the treasure. In this theorem, these zeros tell us about the fundamental structure of the polynomial. This is what we call collapsing the wave function.
because all those intermediate terms vanished.
The theorem dictates that the massive, terrifying 14th degree polynomial simplifies into one single elegant expression.
Which the text says is x minus 1 to the power of 14 equals 0.
That's it. That's the whole thing.
So all of those numbers, the 3432, the 2002,
Yeah.
that was just the expanded version of x minus 1 multiplied by itself 14 times.
Precisely. And this is where your intuition about the numbers 14, 91, and 364 comes back. Where do those numbers live?
Wait, Pascal's triangle.
Bingo. If you look at the 14th row of Pascal's triangle, what do you find? 1, 14, 91, 364, all the way up to 432.
So the polynomial is just wearing a disguise.
A very elaborate one. It was a perfect binomial expansion masquerading as an impossibly difficult problem. And Ezouidi's theorem acted like a DNA test. It stripped away the costume and proved, without a doubt, that the parent was just x minus 1.
Which makes the solution 1.
The root is 1.
It's hilariously simple. We did math in the trillions to find out the answer is the number 1.
But we know it's 1 with absolute certainty. And we know its multiplicity is 14. That means 1 is the root 14 times over. A numerical solver might have hinted at that, but it couldn't have told you why with such elegance.
And the final check, plugging x equals 1 back into the monster equation.
Right. It becomes a simple sum. 1 minus 14 plus 91 minus 364 and so on.
And because those are the alternating numbers from Pascal's triangle,
A well-known property is that the alternating sum of any row is 0. So you get a perfect check.
it really highlights the difference between calculating and understanding, doesn't it?
That's the crucial takeaway. We live in an age of brute force computation. We throw massive processing power at problems to grind them down. And it works.
Sure.
But there's a distinct beauty and I think a power in symbolic computation in looking at the structure of the problem, not just crunching the numbers.
It's the difference between memorizing a speech in a language you don't speak versus actually understanding the grammar.
That's a perfect way to put it. The numerical method memorizes the sounds. The symbolic method understands the meaning.
I just keep thinking about that moment in the middle of the calculation, the k=7 moment.
Yeah.
Staring at these huge numbers on both sides of the equation, it feels like there's a lesson there about trusting the process.
It is. It's about trusting the logic. In math, if your theorem is sound, the scale of the numbers doesn't matter. The rules that apply to 5 apply to 5 trillion. The formula holds the line against the chaos. It ensures the balance is maintained no matter how loud the noise gets.
I like that phrase, the balance is maintained.
Yeah.
It reminds me of signal-to-noise ratios.
It's very similar, yeah.
You look at that polynomial initially, and it is all noise, scary, jagged noise. But if you have the right filter, in this case, Ezouidi's theorem, you tune out all of that, and you're left with this pure single tone, the number 1.
And that's often the case. The most complex phenomena are often just simple rules interacting and iterating over and over again. Complexity is just simplicity in a very elaborate costume.
Which is a comforting thought, really. It suggests that unsolvable problems might not be unsolvable. We just haven't found the right filter yet.
We haven't found the pattern. We're still staring at the coefficients, thinking they're random, instead of seeing they're just the 14th row of a triangle.
So we've crapped the 14th degree, we walked through the fire and came out with a single integer.
And we didn't even need a calculator. Well,
Speak for yourself.
huh.
I might have needed one for the trillions. But we definitely didn't need a supercomputer.
No, just logic.
I think that's a great place to wrap it up. We started with a monster and we ended with a pet.
We tamed the beast.
So for everyone listening, next time you're faced with a problem that just looks like a wall of random chaotic noise, whether that's a spreadsheet at work or, just a complicated life situation, take a step back.